So the first part of this question asks us to identify the dependencies. So a true data dependence is when one instruction creates a value and that value is read by another instruction. And it doesn't matter how far apart these instructions are. If one instruction creates a value and another instruction consumes that value, there's a data dependence between them. So in this case, this first instruction writes T1 and the second instruction reads T1, so there's a data dependence there. And similarly, second instruction writes T2 and the third instruction reads it. The fourth instruction writes T3 and the third instruction writes T3, the fourth instruction reads T3, so there's a data dependence between them. These data dependencies are all within an iteration. So intra-iteration data dependencies. There's also data dependencies that span iterations. So for example, where's the value that's produced and written into A0 that gets read by this instruction? Well, after the first iteration, it's the result of this load. So there's a dependence between that load, this fifth instruction, and the first instruction. So on iteration n, this load will write A0, and then on iteration n plus 1, it will read A0. Likewise, there's a dependence between that instruction and itself on the following iteration. And so these are both examples of cross-iteration dependencies. So those are the data dependencies. And the second question asks us to identify how many cycles on average this loop takes to execute. Say, imagine it's going to execute many iterations. How many cycles on average does it take? Well, I've taken the liberty of already writing the instructions in this table. And the first instruction we're going to just write out because we know it doesn't stall the first time we encounter it. The second instruction, it's going to enter IF in cycle 2 because the previous instruction left IF, and so we can do PC plus 4 and fetch that instruction. It's going to enter ID because the previous instruction left ID, and at this point we still don't know what kind of instruction it is until the end of ID. But because there's a dependence between these two instructions and one of them is a load, it's not going to be able to move into the execute stage in cycle 4. The result of this load isn't going to be available until the end of cycle 4, and so we can't enter the execute stage with this load until that value is available. And so this second load isn't going to enter the execute stage until cycle 5, at which point it's going to complete without further stalls. The third instruction, we can fetch it as soon as the second instruction leaves the fetch stage. As soon as we latch a new PC value, we'll fetch the next instruction. But because the second instruction doesn't leave the decode stage, this third instruction can't move into the decode stage in cycle 4. And so it's stuck in the fetch stage of the pipeline until the second instruction moves on. You can think of this as like a traffic jam, that if one car stops at a stoplight, all the cars behind it have to stop also. But once that instruction moves out of the ID stage, this instruction is free to move in. But just like the previous case, this third instruction is dependent on the second instruction, and that instruction is not producing its value until the end of cycle 6. And so the third instruction needs to stay in the ID stage until the end of cycle 6, and then we can bypass the value when it executes in cycle 7. This branch instruction won't be fetched until the load leaves the fetch stage. So at the end of cycle 4, we'll update the PC with PC plus 4, and so that means we can fetch the branch in cycle 5. Similar to the previous cycle, it can't move forward because the previous instruction stalled, so it won't move into the ID stage until 7. Again, the branch is dependent on the load. The load value is available at the end of cycle 8, and so we need to stall and decode again, and we'll move into the execute stage in cycle 9. So that's the branch. We're assuming that the branch is not taken, that we're going to do another iteration of the loop. And what we see is this load isn't dependent on any of the previous instructions, immediately previous instructions. Although there are dependencies from this instruction to the one in the previous iteration, that's not going to result in a hazard because it happened so long ago. And so we can go ahead and fetch that instruction as soon as the fetch stage is available, but there's not going to be any further stalls due to hazards on this instruction. So it's going to execute as fast as possible. And then the jump loop instruction is an unconditional branch, and so there's no dependencies between it. It's unconditional. We're always going to take it. And so it's going to execute as soon as it can get into the desired pipeline stages. So what happens after this loop? Well, we need to know how many stall cycles it takes us, or flush cycles, until we get to start fetching the first instruction of the next iteration of the loop. We're using a taken or predict not taken branch policy, and so the instruction that's going to get fetched after the jump loop is going to be PC plus 4. It's going to be this move. And so because we don't know any better when we're executing this, we're going to fetch the move instruction. But what happens is at the end of cycle 10, when the jump is completing the decode stage, we know two things. One, we know that we've decoded the instruction. We know it's a jump. And so we know it's an unconditional jump that's going to be taken. And also we can compute the target, because all the information necessary to compute the target, which is PC plus 4 plus the sign extended shifted immediate, all of that's available in the decode stage. So at the end of cycle 10, we know we have a branch and we know where it's going, and we know it's not this move. And so what we're going to do is we're going to flush that move, and we're going to fetch the next iteration of that first load, the load into T1. And so this flushed instruction is going to keep moving down the pipeline as if it were a normal instruction, but it's not going to do anything, and the next iteration of the load is going to get executed. So now we're in a position where we can actually compute how long it takes to execute one iteration of the loop. And the key is to avoid double counting. That in particular, what we don't want to do is measure the number of cycles from the beginning of this process to the end of the process. Because if you think about replicating this loop a number of times, we would end up double counting some of the stages of the pipeline. So what we're going to do is we're going to take two copies of the same instructions for different iterations. This is the first instruction of iteration n, and this is the first instruction of iteration n plus 1, and we're going to pick a stage of it. I like to pick the write back stage. And what we're going to say is, how many cycles did it take between the end of the write back stage the first time and the end of the write back stage the second time. And in this way, we're not going to count any of these cycles twice. So what we see is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 cycles. So that on average, this loop iteration takes 10 cycles.